Alright guys, this is I don't want to teach high school. I don't want to know what it's like to teach high school. So number 49. So 11.9 was that funky section about curvature and trying to use arc length as a parameter. I mean, the math gets a little bit weird looking, like you expect for Calc 3, but 49 is about curvature for plane curves. So show that the curve R of t equals G of t. And these are twice differentiable. So f and g are at least twice differentiable. Has this given curvature, right? So what does it look like they might have done? I mean, what formulas do we have for the curvature? Let's see which ones kind of make sense for what we know. We don't know that much about this. They only give us some general f of t, g of t, right? So which one do you think we should use?
Whenever that with the cross product.
Yeah, so the one that looks like this here. Sounds like it might be a good idea. That one? And if you want to, you certainly can put in here, this is just the second derivative, the first derivative, that's what those mean, right? Velocity is the first derivative, acceleration the second derivative. So what is r prime, which would be v? Yeah, you gotta love this derivative rule. Derivative f is f prime. Sweet. Right. So let me just drop the of t, is that cool?
Yes.
If it's not cool, I'm gonna do it anyway. And then what's r double prime? That'll be a, right? Curvily enough, that's f double prime. So now, you know, that's obviously why they had to say it's twice differentiable. That's why the formula you picked makes sense, because in it, it's got something that you have to differentiate twice. So that kind of matches it up. So now I got to take a cross v. Now that's where things get a little weird, right? The magnitude of a cross v. Why is that? Is that where you had the problem?
Yes.
Why?
Well, actually, I'm taking the opposite order of what we have here, and I tried like more than one times.
But how did you set it up? So my a is f double prime g double prime. My v is f prime g prime. Right?
And making like the small matrices and multiplying. Like
I like it, but the problem is that that definition only works on a matrix that has 3 rows, 3 columns. And they did one example earlier in the book where they had something in 2 dimensions. If I cross I and j, what would I get? K. Right? So if I start with 2 dimensions, the cross product doesn't care. It says force there to be a 3rd dimension. And this kind of feeds into what we're going to do today. If all of algebra assumes what to be true, all of, like math 90, math 110, assumes what to be true about z.
0.
Yeah, z equals 0, right? So actually my r is truly f, g, 0. My r prime or v is f prime, g prime, 0. And my a is f double prime, g double prime, 0. And now you can throw it into the matrix, and it'll actually make sense. You can only do a determinant for a square matrix, meaning if it's got 3 columns, it's got to have 3 rows. The minute you try to set up I, J, done, you got 2 columns and 3 rows. Holy shit, I don't know what to do with that. Is that where the problem was? Because now to do A cross V, it's going to be magnitude of the determinant of I, J, K. A is f double prime, g double prime 0, f prime, g prime 0 for V. Right? The nice thing is you kind of already know what's going to happen here. If I got something that exists totally in I and J, its cross product has got to totally exist in K. And you see that here. Everything is 0 except for the one with the k. So inside here would go f double prime g prime minus f prime g double prime. Right, and this will be, this whole thing will be k. And what's really beautiful about something that exists along a single given axis is its length is exactly there, right? So what's the length, what's this magnitude going to be then? Let me ask you this, what's the magnitude of this vector here? 4. And what's the name of that vector? What's the name of it? Like the name of this vector is blah k. 4I, isn't it? So if it's lying directly on an axis, you can see its length. It's got to be the multiple of that. So what's the length of this? This, without the k on it, right? And isn't that the part of the, you know you're on the right track because that's exactly what's on the top for the answer. So A cross B, magnitude, has got to be how long this is. And then wouldn't it be the square root of this squared plus 0 squared plus 0? So of course it's going to be this, right? So on the top you get this. Of course you got to put it in absolute values because you're going to take a square root of a square. So the top looks good so far, right? Now you just got to figure out the bottom. You've got to take the magnitude of the velocity and cube it and see if that ends up being what they get on the bottom. So it sounds like maybe some stuff simplifies when you start to do that, right? Because the bottom only has a few pieces to it.
It actually works.
It actually works. I know, it's crazy.
But here's in the textbook, the numerator starts with f of prime times g double prime minus f double prime times g prime, which is opposite of the...
F prime. Oh, and it's the absolute values. So who cares? They just did it the other way around. I don't care. It's in absolute values, right? So I don't know which way they did it. Or if they just did that on purpose to see if you knew. They could just turn that damn thing around, right? Absolute value of 2 minus 7 is the same thing as absolute value of 7 minus 2. So that is a little bit evil on their part. I don't think that was necessary to do. I mean, because that's, in fact, yeah. I mean, I took into account the negatives, so this is what you get here. They just decided to say, I'm just going to turn around. All right, cool. So those, to me, those problems are not easy, but it's kind of nice to have a target solution. Right? Prove that this is this. You know, like, okay, thank God, I know kind of like what it's supposed to look like. All right? So I know I'm on the right track if I get one of them at least close, and then see why that's the other way around. Cool. Any other questions from 11.9, or we just barely got to 12.1 last time? Okay. I'm an optimistic fool, so I think that was a good sign. We just barely got into 12.1, and just to talk real quick about what we got over, we got into. And I don't know if you guys get the idea that on that last test, I gave you a problem, and I went over it last time. That problem about find all the form of all the vectors that are orthogonal to this vector I gave you on the test. And it ended up having 2 variables in it, right? So we kind of went over that last time in class. That probably, hopefully, should have helped you make corrections if you had to for that problem. But it makes sense then that would be a plane, because a line has 1 variable. A plane's got to have 2 directions it can go in, so it's got to have 2 variables. And you can keep going with that. That's what linear algebra does. It just keeps going with that idea up to who knows how many dimensions you want. But what do I need for the equation of a plane?
Orthogonal vector.
Good. So I need an orthogonal vector, which in this case is called the what? First I'll give you the name of it. In this case you call it the normal. The normal vector. And that normally has the, if I want to do it in general, it's ABC, right? And a point that the plane goes through, right? So that's kind of funny. In algebra, you learn for a line, you need a point and a direction. So the normal vector in this case does give me a direction. It says, okay, there's the normal vector. My plane must then go like this, right? So it sort of gives me a direction, and I also need a point, so I put the plane in the right place. So it's really beautiful, the analogy between easy-ass math and this weird shit. It's a beautiful analogy. So I need a normal vector and a point. X naught, Y naught, Z naught. Okay. I'm not going to run through the derivation again. They do a good job of stepping it through on page 775. But you end up with that, right? Because this is after taking the dot product, making it equal to 0. If this is the normal vector to everything in here, then their dot product must be 0. So I dot that with what I get when I take out any point in the plane minus this point to get a vector. Right? So I dot those bad boys, and I end up here. Alternate definition would be this here, where D is AX naught plus BY naught plus CZ naught, just some the constant that comes out of that, right? Okay, baby. So, can somebody tell me, for this plane here, what's the normal vector?
4, 7, 2.
Of course, I'm evil. That's not right. The normal vector is 4,
-7, 2.
No, 2 and
-2, -7. Aw, Jeff, that was bumpy. But you know, I'm not necessarily going to do that to you, but you know somewhere it's going to happen. So it's out of order, who cares? It's got to be the A's got to be in front of the X stuff, the B's got to be in front of the Y stuff, so forth. Right? They got to match up. So the normal vector to that plane is 4, 2, -7. So there was a question before about how do I tell when two planes are parallel, right? So if I have one plane that has his normal vector, right? So here's the plane, this plane here, whoop, and there's the normal vector. Okay? Can you guys see that plane? Shut. If you can, good. Either you got really good imagination or you're as crazy as I am. And then you have some other. Now, what's got to be true? If I want to have another plane somewhere, where can I put his normal vector so that these guys would be parallel? So here's one plane here. Pop. What's got to be true when I try to put another plane up there to have it be parallel to this one? The normal vectors have to themselves be parallel, right? So this is a normal vector on top of that plane. If there's another normal vector here for its plane, those planes would be parallel, wouldn't they? And how do I show that these two are parallel? It's much easier than that. To be parallel, they have to be scalar multiples of each other. That's it, right? If this is 1, 2, 3, and this is 2, 4, 6, yay, right? Then they really are just the same vector, just moved longer or somewhere else. That's the idea. How are we doing? How would you show that two planes are orthogonal, meaning they meet at a 90-degree angle? Then their normal vectors have to be orthogonal, and that would just be the dot product equal to 0. Cool. Right? How are we doing? So scalar multiples mean that those vectors are parallel. They lie along each other, right? And a quick word about that. Remember that problem? I'm sure you do. We had this on the test, and you had like a U, and a V, and a W. So some of you guys did put those like back at the origin, here's U, here's V, here's W, whatever, right? Well, if you look at it like this, does that make a triangle? No. Is that where those vectors really are? No. That's those vectors forced into what's called standard position, right? That's why their names are the points that they would point to if they were at the origin. But where are those vectors? They are up here. They do make a triangle, right? So if I have two vectors, one is 1, 2, 3, the other one's 2, 4, 6, you would say like, well, they're both at the origin and the other one's just twice as long as the first guy, but that's not really true. They could be anywhere. But wherever they are, they must be parallel, because if you took it and moved it, then they would lie right on top of each other. One would be just twice as long as the other one. Okay, maybe. So, look at this problem here. In fact, let me see if you guys can get this here. I like this problem. Can anybody come up with the equation of a plane that is orthogonal to that plane? So let me put that plane less evenly up here. That's good, Jeff. And its normal vector, like we figured out, is 4, 2, -7. This is wide open. There's an infinite number of answers, obviously, because so we come up with the equation of a plane that would be orthogonal to this plane. Now, why is there an infinite number of answers? So if I have that plane back there, right, that wall is a plane. There are two planes that I can see visibly that are orthogonal to that plane. What would they be? That wall and that wall, right? And there's even another one. This wall, the ceiling, and that. And then how many are in between all this stuff that I can't see? They're invisible. Thank God. Unless you have a Resident Evil thing that go dead. You guys got that reference? I like it. So I have all these little planes in the middle. There's an infinite number, of course, between there, and then we got an infinite number above the ceiling, an infinite number below the floor, blah, blah, blah. I think you guys are with me, right? So they all meet this at a 90-degree angle. There's an infinite number of answers. So you might think you could just get it by guessing purely. It's an infinite number of answers. But what's got to happen for the other guy's normal, for that plane to be orthogonal to mine? And what's the easiest way to make the dot product? Not to make it 0, 0, 0. That's not really a viable vector to use, right? The easiest way to do it, so an orthogonal normal would be, who's got a good example? What would it be?
1, -2, 0.
Why 1, -2? Yeah, well, okay, that'll work. 1, -2. I love it. So making one of them 0, and then making the other two work. So you should see 4 minus 4 plus 0 is 0. Therefore, any plane that has this as a normal vector would then be orthogonal to this plane. How we doing?
You do negative reciprocals, right?
Yeah, as long as you make one of them 0. The minute that one of them's not 0, it's a little bit more open. There's a lot of ways to make it happen then. So I could just do, one of them is negative in that case. So I could do 1/4, -1/2, 0, or something like that.
-2 or 4.
Yeah, you can do scalar multiples of this, obviously. Any scalar multiple of this will work, right? What else would work here? So this is option 1. What's option 2 would be, make the first thing 0. And then what would this have to be? For example, 7 and 2. They're already opposite signs here, right? That would make 14 minus 14. That dot product would be 0. They would be orthogonal. How we doing? So there's all these little side, easy math things to do that relate to these weirder, big concepts of dot product, 0, orthogonal, all this stuff. There's these little easy math things you can do if it's kind of a wide open question. Give me one thing that does this. Well, shit, there's a lot of answers. Make the math easy, right? Okay. Let's see. What's the other problem I want to give you guys? Oh, what about something that's parallel to this guy? So these would be perpendicular. These would be orthogonal planes. What about parallel planes? That's the easier question.
8, 4, -14.
So if one has a normal of 4, 2, -7, a parallel plane normal would have, yeah, some multiple of that, right? So I'd say 4a, 2a, -7a, and I've just captured all of them, right? Cool. Sweet. Now don't worry too much about, I mean, this is sort of a concern, but you don't, if you want a truly parallel plane, it can't end up being the same plane. Because you are defining where they are by giving me a point. So if you kind of want to make sure that there's some separation there, right? That they don't capture the same points. Okay. But that's not going to be, it's not something we really have to worry about. What do you guys think about this? How many of you guys have done, I think I asked this question before, I think not many of you have done a lot with matrices, is that true? Have you guys done much at all with matrices?
Like pre-cal.
Gotcha. I have a way around that then. I have a way around that because if you've ever done row reducing of a matrix, how many of you guys know what I mean when I say that? Row reduced echelon form. Yeah. Gaussian elimination or Gaussian Jordan elimination. Right? I can do it without matrices, and I can show you kind of a shortcut to this next problem. Let me see what you guys think about for this. Find the equation of the line for the intersection of x plus 2y plus z equals 5, 2x plus y minus z equals 7. So there's two planes. They want the equation of the line for the intersection. What's a good thing to check first to see if there's even any reason to do this? See if they're parallel real quick, right? What's a quick way to see if they're parallel? Look at their normal and see if they're scalable. So do that first, and they won't be parallel, or else there's no reason for this, right? It's a really quick answer then. Doesn't exist. So see what you can think about trying to attack this problem. What can you do to figure out that intersection line? And don't think you get it by eliminating a variable, because, right? What's the line look like in R3? It looks like some vector, position vector plus t times some direction vector, right? It doesn't look like necessarily x equals 2 plus y, all right? You gotta be careful. Just think for a second. Don't say anything yet. I forget what they use. I was going to do something different. No, yeah, I don't like the way they do it. The way they do it is too much work. All right, so some of you guys are like, that's all the thought I want to waste on this, Jeff. So let me try to do this without a matrix. And those of you who know matrices, you can do it a little quicker by setting it up in a matrix. Let me think if I remember which way I want to go. No, I didn't. Between these two, how do you eliminate the x's? What do you do? Yeah, so take this, multiply by -2. All right, so what do we get? We get -3y minus 3z equals -3. Also known as y plus z equals 1, right? Divided by -3. How we doing? Now, I'm about to do something a little different than you've seen. If you've done matrices, you might kind of see what I'm doing. I've just made a third equation, right? And this is something that's not really touched on too much when you do systems of equations, but we've just made a third equation. By itself, it's viable. By itself, it's true. So I can use it to kill like the y here, right? Or the y there. Well, which way? Let's kill the y here. Why not? So 2 is 2x plus y minus z equals 7. You guys kind of with me? This is just systems of equations. I'm just eliminating variables, right? I'm doing something a little bit weird right now. Take the third one, and of course I'm going to have to do what with it to kill the y there? Yeah, I could solve for y and do substitution, but let's stick with elimination. I can multiply by -1. So I get negative y minus z equals -1. So what do you get when you add those together? All right, so you get x minus z equals 3. Cool.
X over 2?
Where are we at?
Oh, never mind.
That's okay. So which variable could I call t because the other two variables depend on it? Z, right? So if I call z t, what's x then? Just replace z with t and you get t plus 3. And what's y?
1 minus t.
All right, sweet. Let's just go. Now, that wasn't really that hard at all, was it? Now, the way they do it in the book, you should be able to do it the way they do it in the book. What they do is they find a point that lies on the plane, and then they use cross products to find a normal, and then they put it together. We don't really need to do that. There's a much better way to do that. Just like this. I've gotten my definition. Why do I know this is a line? Because it only has one variable, right? Everything depends on t. So it truly only has one independent variable is what I mean when I say variable now. Right? So it only has one independent variable. 3 dependent ones, so they're not really variables. Look at the answer they get in the book. And actually, I'm sorry, you guys I don't know where you are. So the last is example 2 on page 775. The answer's at the top of page 776. The answer they get is freaky. Where'd it go? I don't forget where. No, I'm sorry. I'm sorry. The bottom page 777, and the answer is on top page 778. I was off by 1. They get this. They get 3 minus 3t, 1 plus 3t, negative 3t. Now compare that to what we got. We got t plus 3, 1 minus t, and t. Are those the same? Hell yeah. If you just call this t instead, so here instead of plus 3t, I'd put minus t, hey? Right? And here I'd put plus t, hey? It's a different word. Is that cool? I mean, in fact, we got a much better, I like this better than I like that. That's for damn sure. That looks a little nicer to work with, right? I want at least one of them to be just t. That makes everything easier to look at. Okay, I have no idea if you guys are okay with that. Tell you honestly, what we just did is really like part of what you do in linear. You take it further than this, and you go into all kinds of other geometric shapes in whatever dimension you're in. Holy shit. But for 3 dimensions, that's how I get equations. I see how many independent variables do I need. Well, if I need 1, it's a line. If I need 2, it's a plane. If I need 3, it's a volume. If I need 4, it's, hypervolume, or whatever you want to call it.
So why couldn't you just eliminate z?
So once I had this, oh yeah, I could have eliminated z. Oh, in the beginning, no, I couldn't. What I was trying to do is make it look easier to compare to the book. I could have still did it if I did z. It would have come out a little bit harder to compare it here visually, but I still could have done it because mine says y plus z equals 1. And what's there, y plus z? Y plus z is what? 1. So far it matches. I could have matched it that way. I just wanted to match it more directly. Okay. So that's my suggestion on how to do a problem like that. Example, what was it I was actually doing? Example 6. Sorry. That's the one we just did, example 6. You could do it the same way the book does it. Nothing wrong with that either. Either way. Yeah.
I lost you in the plus t's. Where did the t's come from?
So where are we at?
Where did your t's come from?
Here?
Yeah.
So if I look at this equation, this is the one I got that's from these two, and this is another one I got using the equations that I have, right? What do they both depend on? What do they have in common? They both have a z in common. So since y depends on z and x depends on z, x and y aren't truly variables then. They're dependent on this other thing. So I call zt like a parameter, right? And then x is, where to go? X is, add this over, t plus 3, so forth. So when you do this process, if you do it and you get like x plus y equals 7 and z minus y equals 2, well then y would be your t. And then you can build it up from there. Okay. Maybe. If you look through the book, if you look at example 6 in the book and you like their procedure better, I'm not going to redo what they do. You can look at it. They find a point, and then they find a cross product to get a normal. And that's the two things you need for a line to get it by definition. I got the line equation not by definition, just a little quicker. Okay. And really, what does it mean when you have a system of equations? When I look at this as a system of equations, what does that mean? And that's kind of a vague question, but that means that both of these are true at the same time. Isn't that what I want to have happen? The intersection is going to be where both of these equations are true at the same time. Right? So when you do it in 2 dimensions, I have one line, it's all the points that work in that equation. Another line, all the points that work in that equation. Where's the answer? Where they're both true at the same time. That's why setting up a system of equations works. Gets you the point where they meet. Here I want a line where they meet. Well, it's the same idea. I should be able to do it the same way. And there it is. And that, I think, is a little quicker than the way the book does it. Okay, so now, let me see. What I want to do is I want to talk a little bit about this idea. I've got a handout for you guys to work on that tries to bring this together. What you're going to have to do in these sections, in the next few sections, is you're going to have to draw in 3 dimensions, which is not the easiest thing to do. And as the person, yeah, that's a good point. As a person grading this stuff, it's going to be hard on me also. So, yeah.
It would be easier if you use isometric paper too.
Yeah, if you have some. Do you have some?
I have a PDF. I can send a PDF file to everybody.
You can also just search Google image search. Yeah. Okay.
Yes, Steve.
So guys, if I said graph x equal to 1, and I told my Math 90 students to do this, what picture would they come up with? So some of them might do this. Yay. Right? And in a sense, that's correct, because I wasn't very specific in how many dimensions I want this in. How many dimensions could this be? Infinite. Could be anywhere from 1 to n. Pick your own n. So that's one example. What I should probably mean in Math 90, of course, would be what? And what do you do to extend this idea into what you're just now saying? All that's got to be true is x is equal to 1. So if I want to extend this, that means y could be anything, right? So really what I end up doing is, and this is sometimes what I try to show people sometimes, is you could have another one up here, this is y equals 0. Because that's what you told me. That's kind of like, this is kind of like what you're assuming when you're doing this. It's really a question I had earlier about what do you assume when you graph anything in the xy plane? You assume z equals 0, right? So this would be assuming y equals 0. At y equal 1, it'd be in the same place. Y equal 2, and so then you just connect them all together, and of course that's what you end up with. You have, doing it the normal way, you'd have, right, so you can imagine all these infinite number of little number lines going up and down. So to extend it for us this might mean what? A plane. And notice something real quick. That line is how related to the y-axis? It's parallel. If I would have been missing an x, if this would have been y equals 1, it would have been parallel to the x-axis. Interesting. So actually that idea holds true. If you're missing a z, it's going to be parallel to that plane. I love it. If you're missing an x, it's going to be parallel to that, so forth. Right? The same idea here, thank God. So I would extend it into 3 dimensions. If I extend it into 3 dimensions, right? I don't need all this crap. Right? So all it has to be true is x has to be 1. That's all it has to be true. So now the thing we did there is sort of like this, right? Because whenever I look at an xy plane, I'm really like looking at that. Cool? But now what can happen is z could be anything also. So y can be anything, goes crazy this way. Z can be anything. Now it goes crazy. Now I've turned it over, up and down on the z-axis. So now I get this plane here. I can extend down. So I get that plane, right? And you can see how little artistic ability I have. Which is why I thank God while you guys are working on the handout, I'm going to pull up. They have interactive figures from the book, and this is definitely where I need them. So and you can actually rotate them, thank God, because sometimes it's hard in 3D if you're looking at it from the wrong direction. So if I rotate, you're like, oh, cool, that's what's going on. And what these are called, let me give you a little bit better example here, a little bit more interesting example. So now you can extend this idea. If I say graph y equals x squared, of course, we all know what it looks like on the xy plane. But I'm talking about graphing it in R3. So the idea still extends. The idea is the same. So this in R2, every time I say that, I think about Star Wars. So in R2, you're going to have this parabola. Well, what do you think is going to happen in R3 then?
So it's very curved plane.
So here I've got, let's try to make this in 3D. Here I've got my x, y plane. So that what I've already graphed up there would be this. So here's 1, 1. Here's negative 1, 1. Here's 2, 4. Negative 2, 4, right? So here's that parabola I drew up there, just kind of like smack, right? And you guys see what I mean by it? You guys, hopefully everybody has seen that is the xy plane if you just stood above it and looked down on it, right? So now what can I do to extend this idea? Which variable is missing? Z. So all I have to do is take that shape and make basically, all the lines through the points that are parallel to the z-axis. Of course, the next level of this is what happens when no letters are missing. And that's how you get these closed shapes. Do you see how z is missing? Therefore, z is allowed to be anything. And that's why it just kind of extends. And you end up with something that could be like a prism, because a prism is a repeated shape forever, right? So the prism is kind of a straight on all sides. So to make this shape then, a good idea to make this shape is to kind of just take everything and move it straight up here. So here, like if I'm at z equal 1, I would go right there, just kind of extend this shape. I'm going to do it terribly. Oh yeah, this is really horrible. But oh well. Look at page 779, a little bit better example.
Wow.
Yeah. So thank God I can just put some stuff on the computer instead of trying to graph it.
Just layer them. Just have
What's
it
that?
cross onto it.
Yeah, this is horrible.
And that line just make it cross back onto it.
Yeah, it's a little silted on the bottom. Oh, they don't even show you that. It's too bad. Oh, they do a little better job on the one on the bottom.
I can see it.
Oh. So if I had something like this, x squared. If I had something like that. Yes. Oh crap. So all your parabolas, your parabolic, your conic sections. Remember those? Circles, ellipses, hyperbolas, parabolas. Oh yes. They're all coming back to haunt you now. So in the xy plane, what would this look like? So I already know it's an ellipse. Be more specific now.
It's an ellipse with x4, y2.
Exactly. Cool. So the x is going to go out to 4. And you can see that because if x is 4, that makes 1, y would be 0. That makes sense. So it is truly just the one with the bigger one goes out further. Right? A circle would have both of these the same. That's why it's symmetric in all directions. And then on the y, it'd go up 2 and down 2. So here's what it would look like in the xy plane. All right, Jeff. My football's been through a lot of work. And then to extend that, to 3 dimensions. Here's my x, my y, my z. So again, z is totally missing, which means it's going to be a cylinder. So they talk about this in this book. If you have a trace and it's missing a variable, that means it's going to end up being officially what's called a cylinder. So I know for us, cylinders are like paint cans and such, but it's a little more general for graphing these functions. They're actually, anything that's sort of like if you cut it, it's the same cross section, right? That would be the cylinder. So this is going to look a lot more like a cylinder than something else earlier would look like. On the xy plane, it was 2 on the y, -2, 4, -4. So there's what it looks like there. All right. Then you go up here and you think, okay, now if I'm up here, it would be, oh, let's see if I can do this. There. Okay, this is going to get interesting. Okay. There. There. And there. So let's see. Okay, that's beautiful. Oh, if I just didn't make this boxy. Then you can connect these sides and up and down. So thankfully, if you look on page 779, I should give myself more room in between, I think. That'll make it easier. At the bottom of page 779, they show that. They show you the traces inside, and they show you just connecting the outside. So really, all I'm going to want from you guys, I didn't give myself enough room here. That's my fault, but too bad for me. So if you have this, and you give yourself a little more room, and that's really all I need is like a trace, and then just connect the outsides. That would be the idea. It goes forever in both directions. So you just have to have a couple of traces, and then you can connect them. You don't have to try to make the shading on the outside. That's crazy, right? So what I actually want you guys to do is, before I even talk about them, here's an example of one that's not missing any letters. Yay, Jeff. So I kind of step you through the steps here. I'll tell you honestly, this is actually a little bit easier, because then it's kind of constrained in all directions. You don't have this vague, like, connect the sides idea at the end.
What's going on here? I'm not going to be able to draft these. I give up. I'm not even going to try. Like, I can't. That's as far as I can get. That's it.
Oh, sorry.
Quadrant? Oh, right.
Like Iron Man, he makes a suit.
First Resident Evil, now Iron Man. Interesting, very interesting.
Yeah, in 30 years, every student's going to be required to have those gloves.
I know, right? You're gonna have like a computer, but it's gonna be like see-through, you know? And then you're gonna be like moving
So on the
stuff
desk, you'll
inside.
have these things that drop from the ceiling, so nobody else can see. Except me, I can make it visible. I can say, oh, you're doing that. That's wrong.
Yeah, I know, right?
No, that's wrong.
That'd be so cool.
I can't wait. I'm still learning.
So is it okay if I shade it as that? Like,
Get out of here.
as if it is a cylinder, like shade the scenery?
Oh,
Or
I kind of see what you're doing. Just gotta make sure that
I just made it like.
it's not really open. It's not really stopping there. It goes forever in both
No, I know
directions.
that, but is that okay?
That's sort of like what they did, so I mean that's fine.
Oh, yeah.
Because they kind of let this top open, but it's understood it goes forever. Yeah.
Yeah, because it's easier for me to visualize it that way if I shade it in.
No, it's fine. In fact, that looks pretty good. I can see what's going on.
Alright,
So I'm not going to complain about that.
alright.
Oh.
I have no idea where to start.
Number 1, 2, and 3 should be easy, yes.
Should be.
Number 4 is the one that might be a little hard, but that's why I'm hoping once you do 1, 2, and 3, just think about that plane is now here, do the same shape. That plane is now here, do the same shape.
I don't know how to look at it.
No.
X squared, but get out of here. So let's see the Y too. Yeah. I think you should be like required to take art before you can like.
I like that.
The way
The art guys are like that, and definitely they fill in classes.
that's true.
I'm not saying they don't now.
Yeah, I can barely draw stick figures. This is bad. How we just focus on drawing a curved line. You're kind of get points or what?
I've succeeded in getting friends. Your skills are way too high. Yeah.
Who cares?
Oh, I
That's amazing. I'm stuck. This is hard. I'm looking around at other people.
You and your I'm sorry. You know enough percent like this.
Sure.
They give me two dimensions. They can say there's like thing Z is one. You want me to wrap here or put it in straight line?
No, Z is one, there's still only two variables. Z is now just got one.
It's just closer together.
And then plug in X and Y to each other. Oh, okay. Oh, no, it's two more.
X, Y, axis.
Oh, I see what they did there.
Good. I like mine.
But when F equals to 0, it's not the same shape.
No, I'm just imagining it. Careful, man. Really careful.
Taylor takes too long. I feel like it's
It's like looking at it from each side, it's a triangle, and then looking at it from above, it's a circle, or like
I have no idea.
It's like a boat.
except for it's not quite like this one's like a cylinder. If they're good position.
Really, Taylor? Really?
No, I understand.
It's a cylinder or like the cylinder.
Oh, hold on, hold on.
I got this.
This is X, Y.
Yeah, I didn't draw the top.
So you guys with me here?
Sassy.
So you get z equals y squared over 9 for number 1, when you let x equal 0. So here's my yz plane. At 0, it's 0. At 3 squared, I get z equal 1, Jeff, there you go. 1, 2, 3, there you go. So it's a really fat parabola. Alright, so there's one thing down. So y equals 0, now you get z equals x squared over 4. So again, it's a parabola. But now at 0, 0. At 2, it's 1. Negative 2, it's 1. At 4, it would be 4, wouldn't it?
Yes.
4, it's 4. Negative 4, it's 4. How are we doing?
Look at that.
Alright. So if I look at it from, if I'm standing here, looking at it the xz plane, it's going to look like that. A not so fat parabola. If I stand here, it's going to look like a fat parabola, right? So it's kind of interesting. As you turn, then, it's kind of going from fat to not so fat as you turn. As I turn on the yz plane, it's fat. As I turn it, it's skinny. Right, so it's hard to get the things in the middle, though. We just kind of connect those together. What about this one? This is a little bit weird. When he says z equal to 0, who sees what happens there? Z equal to 0, I get x squared over 4 plus y squared over 9 equals 0. The only way that can happen is if... Careful. It's the only way that can happen. If y is anything bigger than 0, is there any way that could work? Or anything not 0. If y is 1, I can't make this negative 1 to kill it. I'm not talking about complex numbers here, right? The only answer then that works is what?
0, 0.
0, yes. They both have to be 0 in order to make that work.
Got it.
Cool. All right.
Yep. Cool.
So then this, if z equals 0, then you get the point 0, 0 in your xy plane. But so that's why I said, okay, something more interesting then. And one little thing that come out of this is what's got to be true about z? What's like the domain of z? Yeah, it's got to be 0 and up, right? You can't have any negative inputs in there because you got squares on the other side. So it's going to guide me when I want to graph the final answer. I know there's going to be nothing on the bottom of this graph. It's got to be up here for 0 and positive z's. So what happens if z equals 1? And then I get x squared over 4 plus y squared over 9 equals 1, which is the traditional formula for an ellipse. Yeah, now I get an ellipse. And if I let equal 2, equal 3, equals 4, I'm still going to get ellipses, right? Anybody have any idea what happens to those ellipses? Cool, I like it. They're just going to get wider and wider because it starts at a point, 0, 0, 0, really at the end. I'm going to put it in 3 dimensions. And then it goes up and they get wider and wider. The cross section, if I cut it, it's going to look like an ellipse. Okay. Because think about this. I know it's going to be circling the z-axis because that's the one that I'm letting equal 0, equal 1, equal 2. So this ellipse is going to be around the z-axis as it goes up. And my parabolas are going to be going in... Hang with me. So this would look like what? X would go out 2, negative 2. 3, negative 3, 2. Alright, so to get this all put together, this is my YZ trace. So like I was saying earlier, my YZ plane now is here. So what happened to the YZ trace? It's going to be 0. Then it's going to go like at Y for negative 3, Z is 1, right? So y equal negative 3, 1, 2, 3, z is 1. At y equal to 3, it's also 1. 1, 2, 3, it's 1. So it's 1, 2, 3. How are we doing?
Wait, what?
What's going on? Oh, 1, 2, 3. Oh, sorry. 1, 2, lose it. 3, there.
Oh, okay.
How are we doing? Okay. Bye.
You just did. You were right. You were right the first time.
Yeah.
Fine, yeah. 1,
This was about
2, 3.
You got it right the first time.
Oh yeah, up 1 there.
And then
That's
up
fine.
1.
Up 1 from there. Up 1 from 3, exactly. Thank you. So again, I'm looking at it YZ. So
Wait, is it on the 2 or the
The point on YZ is 3, 1, 2, 3, up 1. Not out 1, that would be in the X, like even the negative XY plane somewhere weird. Right? It's the YZ plane. So if I go 1, 2, 3, I've got to go up 1 from there. Cool. And of course, that's the hardest part about this 3D is that Z-axis. Because you got to think kind of sideways when you go up and down that Z-axis. Everything's kind of at a tilt. That's what makes this not terribly easy. So that's not there. As much as it looks like it's there, it's not there. So that's my YZ there, right? Here's my trace, then in the YZ plane. So this point, where's this point shadow for that point? Where would it fall? It would fall right there on top of the 3. So the point is 3Y, 1Z. So it's straight up from the 3. Okay, cool. What about the XZ plane? That's going to go like this. So 0, 0. If X is 1, what was it, 2, then Z is going to be 1, right? If X is -1, -2, Z is going to be 1.
Oh.
It's almost like it's almost like those magic eyes thing. It's almost like it's just got to click. So if I go 2, 2 squared is 4, divided by 4 is 1. I go 1 up, straight up from the 2. Right? Because my Z-axis is straight up and down. If I go back 2, I want to go 1 straight up from that. So now I'm basically putting that first picture, I'm taking this first picture, taking it and moving it around to fall, get up there, bam. So right here, that's the first picture. Like I've taken that first one and I've turned it around. So I'm seeing it from the side. So here's this one. Now that line I just drew, that parabola, it exists in that specific parabola right there. Where's that arrow directly over, of course? The x-axis, right? So it's, of course, if I drew that with no context, you might think it actually exists like down here, possibly. That's another thing about 3D. You've got to kind of keep the context with you. What's the last thing I could do here? What do we do? Z equals 1. I get this shape here. So for z equal to 1, here's what's cool about, this is why I like, and I just Googled XYZ system, and one of the images I got was this. And I think it's really awesome because it helps out when you go up to 1, you want to go, so now I want everything to be at z equal to 1. So let me maybe do this in green. I don't know if you guys, yeah, color sheet. So now if we go out, so at 1, where do I want, this is my yx. So x goes 2 and -2, cool? X goes 2 and -2, right? So at 1, I want to go over there and over there. And see where that's nice. It's supposed to be connecting with the traces on the side here, right? So that's nice to see. And what happens in the y direction? 3 and -3. So there's my ellipse there. Oh, that's terrible. Holy crap. That's really disgusting. So can you, now I need you to try to imagine this. You start with a point, and then you get this tiny little ellipse, and another tiny little ellipse is a little bigger, and another tiny little ellipse is getting bigger. And that fills in like this framework. I think about it, this is like chicken wire, and you're coating outside this paper mache ellipses. As you move up and up and up. So like you told me, if I keep making this 4, 5, 6, they're going to get bigger and bigger ellipses so they can reach around this wire here and go up on the outside. So let's actually see this in a little, let's see this from the book so we can actually see what's going on. Not with Jeff's attempt at art.
It's like
It's
so cool.
Yeah, let's see yours. The 3D drawings.
It's like just
They have like little dogs and cats in there.
Yes.
And stuff.
You're gonna have to make this like,